Okay, so let's try to do the last lecture in 1 hour. Yesterday I derived a kind of expression for the two-point function in general quantum circuit. We used only unitarity, and if you are really implementing unitarity, this is actually written now in the folded picture. So operators are now like states, which are represented by nodes of this diagram, right? By let's say boundary conditions. And in order to not to worry about normalization, actually we can conveniently introduce the following normalization convention. Where we say, okay, what we mean by this bullet is, of course, something which in the folded picture has two wires, right? And then it contains the operator here. For example, here it was like I and I prime, the in and out wire. But for me now, this will be a matrix element of an operator divided by square root of the local Hilbert space dimension. And what I call an open bullet is just, wire which is closing. Right? It's just closing Brian the K copy of the folding picture of the operator dynamics. And this I will denote as, this will be just a kind of, again, I prime. This will be just Kronecker delta, but divided by square root of d. So in this way, I don't have to divide by 1 over d to the number of qubits, because anyway, once we facilitate unitarity, we don't know what was the original size of the system because it drops out, right? You see, everything which is bigger than, for sufficiently large system, everything outside of these light cone domains which are intersecting, right? Now we should really think of these two light cones, right, being intersected, right? And now we have 3 by 4. In this particular picture, this is an example. There are 3 by 4 gates, right? And this rectangle has, this rectangle has shape, which is the sizes which are given by the time plus the difference of coordinates and time minus the difference of coordinates. So it degenerates into a light cone when x minus y is equal to 0. Yeah, when x minus y is equal to 0. When x minus y equal to 0, it's symmetric, it's a square, right? It's the worst case in the sense of computational complexity. But when x minus y is equal to plus minus t, right? Then it degenerates to, one should be a bit careful. Maybe it's plus 1 somewhere, right? Because it should not go to 0, but it should be 1 in one of the two cases. But I don't want to be picky on this. It's just that, you can clarify it for yourself. Yeah, please.
Is W U dagger tensor U, or that's transpose and stuff because of the vector?
That's a transpose. Yeah, exactly. Yeah, that's because we are folding, right? We are folding, so we are flipping things upside down, right? So you get the transpose for the matrix. Yeah, yeah. Okay, now we are kind of ready to try to simplify these things, right? We have used unitarity as much as we could. We still get something which is hard. Yeah, this is to compute this. No one knows a general recipe, right? Google was actually relying on this quantity being hard when they demonstrated so-called quantum advantage back in 2019, where they used this type of circuit where these gates were random. They were sampling this kind of objects, but yeah. So there is nothing really known how to do it in an efficient way. So this kind of quantity is supposedly be exponentially hard to compute. Now, what we will try to do now, we try to now make additional simplifications, and we are trying now to look for properties of gates which would allow to make sufficient additional simplifications in this many-body dynamics. And the key concept here is what we call dual unitary gates or dual unitary circuits. So this will now be the second part of my lecture number 3, which is, technically I'm doing lecture number 3 only, and probably lecture number 4 will be, for all those who are interested, relegated to the tutorial. So I'm probably doing just the lecture number 3 lectures in my regular lecture time. So dual unitary circuits. Okay, so now we want to have additional structure, right? So now let's say we take again our gate, right? Original gate, not folded yet, which maps state ij to state kl, right? And this is the way we imagine it, right? This is the way we imagine time, right? But now we try to think of time also in this direction. We try to say, okay, now let's see what happens if we denote, if we propagate in this direction. So we'll define a gate which propagates in this direction, meaning we'll define a tilde gate which will take states I and k and map to states j and l, right? So we just turn the head 90 degrees, right, and look at things the other way. So we do this particular reshuffling of indices. And what we do now is require that reshuffled gate, that tilted gate, would be unitary as well. So we require unitarity of both u, which is unitary from the outset, and u tilde. This is what we define as dual unitarity, right? So what does it mean to have unitarity of u tilde? Well, let's try to see what would that mean. I mean, we want u tilde dagger u tilde to be u tilde dagger to be identity. So this is just some, for the time being, just some ad hoc condition we require. It's not clear how special it is. It will turn out that it's not so special you might think at first, right? I mean, you think, okay, these are many additional conditions, so maybe there are not even any non-trivial solutions. It turns out that there are not so many fewer solutions when you require this additional condition than if you just require unitarity. It turns out that you just fix 2 additional parameters if you have qubit gates. So, I mean, I hope I'll come to that to discuss this more in detail. But so what does it mean in terms of diagrams? Again, it's useful to write diagrams, right? So now we have this gate u and u dagger, right? And unitarity would be just to connect these 2 guys. But dual unitarity would be now like going from sideways, right? So connecting these 2 guys, right? These 2 guys. I mean, if you just think for a while, this is, if you just write name indices like we usually do. So this is what like ik, right? The same ik as here. Now let's call this k prime and I prime. And multiplying u tilde and u tilde dagger would be like connecting these 2 indices and requiring this to be Yes, it's okay. No, it's I don't know how you like it, but they should look in the same direction as before. So this is k prime k, and this is I prime. So what we want is delta I prime, delta k prime. Okay. So now this looks a bit cumbersome. So let's write the same condition in terms of the folded gate. Again, just imagine this diagram to be flipped, to be cut here, and this folded upwards, right? Then U transpose gets tensor multiplied with U dagger, which is exactly W. And then what we are doing here, we are just doing the closing the 2 gates. So we are just inserting this kind of little bits there. And then we are doing also this thing, right, identifying this and this, which is again just doing a circle like this. So what we are doing basically is taking W and we are requiring this to be equal to that. And then, of course, this is one of these 2 equations, right? The other equation would be just doing the same from the left-hand side. But I will not do it in the original picture. I'll just do it in the doubled picture. So we'll have this, right? So these are diagrams number 3 and number 4. I remind you from yesterday, we already had diagrams number 1 and 2. I'll just put them again on the board. So whenever you see two adjacent circles, empty bullets, pressed against the gate, you can just pull them through and annihilate the gate. So that's the rules of the game now, right? I mean, you have simple game. The question is how much you can simplify the circuit, right? You have a couple of rules, and then you're trying to simplify. And OK, so it's rather straightforward now. The rest, what I'm going to do, is very straightforward. So this was unitarity, right? Unitarity, and this is what sometimes we refer to as space unitarity. And both conditions combined is what we call dual unitarity. And now let's make a couple of examples how much we can simplify things, right? Let's take an example. Let's take a circuit which has 2 by 3 gates, like this. It's again a rectangle, 2 by 3 rectangle. Again, here we'll have A operator, here we have some B operator, and everywhere else we take. By the way, I mean, I probably didn't explain enough, but you still remember yesterday's definition of correlation function. Correlation function is a trace, right? So these bullets below come from kind of come from initial operator, right? Because it's a local operator, so these are identities, right? This is operator times identity. These bullets above are coming from the trace, right? Trace means just connecting 2 sheets, right? And in the picture that we had, the upper bullets would be trace, the lower bullets would be identities, but they are really the same thing, right? Once you look at this folded picture, they're the same thing. So trace is just dual to identity, right? Yeah, there's not more to say, but this picture is really kind of convenient, right? It doesn't require you to think much, right? You just use rules and construct things. But I just want to remind you that these bullets kind of have 2 different meanings. One is identity operator, the other is the trace. Okay, so now what do we do here, right? Now, look, I'm now just using my whatever cloth to erase things, right? I use the rule number 4 to erase this guy. And of course, I have to carry on 2 bullets. Again, rule number 4. Now, of course, I used unitarity. I used rules number 1 and 2 already, right? That's how I produce this rectangle. So I only use 3 and 4. Again, we use rule number 4. Then, okay, here I cannot do much, right? This one is hanging. I cannot do much because I have just 1 bullet here, which prohibits me to do anything. But here I can still do stuff. Then I can use rule number 3 to simplify this guy. Here I have this. What is this? What is this thing? It's trace identity, right? But the way I define normalization is trace identity divided by square root of d square, which is d divided by d square root of d square, which is 1. So that's 1. Okay. Now what I do again here, and I do again here, and I get this. So what do I get now? What is this? This is trace of A. This is trace of B. Well, I mean, I didn't tell you, but it makes sense to do correlation functions only in traces observables, right? Because the traceful observables will just give you trivial constant, right? Or in other words, you can think of just computing connected correlation functions. So we are assuming traceless observables. The result is 0. And now you can just think for a while, and if you are not, if you cannot just deduce the most general rule out of these pictures, then you should check our papers. But I mean, I don't want to formalize now very much, but you can just think for a while, and you will realize immediately that the only way in which you not get 0, you don't reduce these diagrams to traces of traceless operators. The only other remaining way is when you place operators at the ends, at the 2 ends of a light ray, right? For example, like these ones or like these ones. This is the only remaining diagrams. non-zero diagrams. That means correlators. Each diagram means particular space-time correlator, right? And only two diagrams which remain are these ones, where operators like this. Or like this. And in this case is where x is odd, because you remember how I enumerated sites, right? I mean, this is a staggered brickwork circuit, so these sites were odd, like 1, 3, 5, 7, and these were like 2, 4, 6, and so on, even, right? So this means x odd, and this means x even. And in this case, this is y, this is y. So in this case, y minus x has to be plus t, and in this case, y minus x has to be minus t. So these are the two light rays. These are the left mover and the right mover, the right mover and the left mover, right? So we have this very kind of strange, very degenerate way of, everything either decays to zero immediately or it is non-zero only along light rays. So we can now just summarize and write a general formula before we try to interpret a little bit more physically. So the general formula would be then, okay, so now first we can write this, okay, so what it is, what is it, right? I mean, one thing we should immediately realize is that this diagram, well, let's pick one of them, let's pick this diagram. This diagram can be understood as iterating. So let's define a machine which takes the input here and spits output there, right? That machine is just nothing but, it's something that I already discussed in my lectures in the beginning. It's basically, you can write a Krauss, you can write other representation, but it's just a completely positive map, right? It's a completely positive map, which I will denote as M plus. And what does it mean? Well, I mean, how does it act? I mean, you can immediately, this is like an operator, right, which you put in here. So M plus on the operator A, what does it do? It's like, if you write again the full picture, right, this would be the U, and this would be U dagger. This is an A, which you plug in, right? And here you do the trace. So here you put identity, right? Here you put A, here you put identity, then you put the trace here, right? So what is it? This is just M plus of A is you take A, you put U dagger, A cross identity, A dagger A, and you take a trace over the is it correct? I do the trace. Yeah, it's correct. And you do the trace over the first guy. This is a partial trace, right? You have an operator which is defined on 2 qubits. You take a partial qubits. You take a partial trace with respect to the first one. You get something which is local on the second tensor product space, right? So that's just the way how people in quantum information would write a generic completely positive map. This is one of the generic representations of completely positive maps, right? So you can write, well, this is not completely general because here you put identity, so it's a unital map. And it's a very special CPM because U is supposed to be dual unitary, but still it's just a completely positive map. I mean, it's something that maps density matrices to density matrices. In our case, we are not thinking of density matrix, we think of a kind of a dual of completely positive map, which acts on operators. Yeah, but still, it maps operators to operators. It's kind of a Heisenberg picture, but it doesn't, in this case, for this kind of symmetric, completely positive map, the Heisenberg and the Schrödinger picture are looking very much similar. Okay, so now this is M plus. This is just iteration of M plus. And then we can analogously define the M minus, which is this, which is here under this diagram. So M minus just means it moves to negative direction, M plus moves to positive direction. Sorry, this is a bullet. Okay. And this is M minus. Again, M minus on A would be trace of the second one, U dagger 1 cross A U. Okay, so now what is it? What is this now? Well, the correlation functions then can be written then as we have a general formula for correlation functions. How should I convince myself not to press so hard? Okay. Right, so now we are checking, well, I mean, if you want a general formula, of course, you can write just an indicator function which checks whether x is even or odd, right? So if x is odd, this will be something like that, right? And then it checks whether y minus x is equal to t. And then we'll have trace of b times m plus to power t of a. Okay? So that's this expression, right? You take a, you apply m plus 3 times here, and then you trace it, then you multiply with b and trace it, right? So these are the two light rays, and the second one will be checking if x is odd, even. And then we have m minus, okay, to power t. Okay, and then, okay, I mean, it's really simple, right? And again, we should just, again, take a deep breath and try to understand what it means, right? It means that you have a coherent many-body dynamics, which I will claim in next couple of minutes can be completely chaotic, and to explain what I mean by that. But for the time being, we just have a coherent many-body dynamics for which correlation functions, well, will decay. At least they can decay. I mean, then again, we'll have to discuss properties of this completely positive dynamics. But remember, these A and B are traceless operators. So generically, these guys will be exponentially decaying. So we have, and basically, they behave like a quantum Markov chain. So quantum Markov chain, if it's chaotic and ergodic and mixing and so on, the correlation function will decay. So the decay of correlation functions in a completely coherent dynamics, I mean, okay, I mean, of course, we all expect it, but still, I mean, it's very nice to see that it comes out rigorously, right? Without any additional assumptions. And even more, I mean, this is a many-body dynamics, and it's strongly interacting dynamics, but the two-point function behave like a kind of a single particle, which is trapped in the environment of the rest of the system. I mean, it's like the rest of the system acts as a perfect, what people would call a Markovian bath for the dynamics of a target qubit. So we have a target qubit, its correlation spread, with speed plus or minus 1, but it's damped because it's observed by the rest of the system, right? So, I mean, please do ask questions if anything what I'm saying sounds crazy to you or you want to clarify. But let me just make additional physical interpretation of what we have just discovered. Of course, now we did some algebra, right? And maybe you don't want algebra, you just want to have pictures, right? So there's also pictorial representations, right? And well, we have learned already from the, for general kind of local quantum circuits or for general local interacting quantum systems, there is Lieb-Robinson theorem, or there is a simplified version of Lieb-Robinson for circuits, which is rigorous and exact. I mean, Lieb-Robinson theory is, of course, rigorous as well, but there are approximate corrections. In any case, so what we have now is unitarity, which means we have an operator A, and now we look at correlations in space-time, right, which spread from this operator, and these correlations can spread within light cone due to unitarity, right? But then we have also dual unitarity, which means you can flip the head for 90 degrees, and we can also look at dynamics emanating from A in the space direction. So which means that the correlations, whatever, I mean, the effect of the signal, whatever, can spread also in the space direction, right? Only, right, because there is a light cone, right? This is space unitarity. And then you have just the intersection of the two, because we have both unitarity and space unitarity, which means that correlations can only spread on the light rays. Right. So that's a very simple intuitive picture, right? You don't have to, if you trust your geometric intuition, you don't have to do calculations. That's what should follow from what we have. Okay, right. So okay, so now let's discuss a little bit more on the properties of these completely positive maps. What type of properties they might have. So as I said already, M plus and minus are unital. If you want unital trace preserving completely positive map. And you can also think of them as linear maps. They act on d-square dimensional space of single-site operators, right? So they are d-square by d-square dimensional matrices. You can think of them as d-square by d-square dimensional matrices. And since that they are unital, they always have this property that they map unit operator to unit operator. This is the only traceful operator, and for the rest, you can decompose this map in this, I don't know, in the, if you write them in the, let's say for t equal to 2, if you write them in 1 sigma x, sigma y, sigma z basis, so in the basis of Hermitian 2 by 2 matrices, then they are real, then they have real representation, then M are real 4 by 4 matrices, and they have the following structure. They have element 1 here, and then there are 3 by 3 matrices here. So they don't couple identity to anything else. Identity is a left and right eigenvector, right? It's a unit, left, right, being right eigenvector means it's unital, being left eigenvector means it's trace preserving. So the only non-trivial part of M is in this 3 by 3 corner. So there are 3 other eigenvalues. Well, I'm talking about d equal to 2, but of course for larger d it's just a bigger piece here. But this is a finite dimensional linear algebra, so you can do it exactly, either on the computer or even by pen and paper for d equal to 2. And so basically you have a spectral decomposition of this matrix. Of M plus M minus. And you can write it as M plus minus is lambda j, sum over j, eigenvalue lambda j, and then there is an eigenvector uj, and then there is another eigenvector, call it vj. So these are the two operators. Of course, you can think of them as vectorizations of two operators. They are not the same because one of them is the right eigenvector. So M plus minus Vj is lambda j Vj, and the other is the left eigenvector. And Vj uk is delta jk. They are bi-orthonormal, right? So you can always choose for any matrix that can be diagonalized. You can choose the left and the right basis, and they have to be bi-orthogonal, right? This is of course very simple because matrices are 3 by 3. It might happen that this matrix cannot be diagonalized because it's not a normal matrix. It can have a non-trivial Jordan form, and then you have to worry a bit more. But let's assume it can be diagonalized, right? And let's assume that lambda, so these guys j go from 0 to d square minus 1, right? And let's assume that lambda 0 is always the trivial eigenvalue. And so v0 then corresponds to vectorization of a unit matrix. So this corresponds to a trivial fixed point, right, which is corresponding to traceful operators. But we are not interested in that. We are interested in the other. Okay, and I will now say a bit more about what this means, what kind of spectra we can have, and how does this fit to ergodic hierarchy. Because now this is very similar to what people in classical dynamical systems also discuss. They can map this. Sometimes people in classical dynamical systems can map a system to a Markov chain, And then the spectrum of Markov chain determines ergodic and mixing properties of dynamics in relation to the possible decays of correlation functions. So this is all very similar here, but before going to that, let me just make now a footnote remark or a footnote discussion, which is about complete parameterization for d equal to 2. For d equal to 2. So for qubits, right? For qubits, I mean, we can ask this question because it's something that, well, disturbed us at least at first, right? How generic this is, how special, how fine-tuned it is. So let's try to see what is the most general manifold of dual unitary gates for certain Hilbert space dimension, let's say for qubits. And then there are a couple of things which are interesting to observe. First, there are two claims which are easy to prove. The first claim, which is useful, is to say the following: U is dual unitary if and only if U times a permutation, U times a swap, has a unitary partial transpose. So if U times P, I denoted P as you remember from my first lecture, P was the permutation of two sides, right? So U times P, and then there is an operation which is also very kind of popular in quantum information theory, which is called partial transpose. You just transpose part of the system. So this is, of course, defined on a tensor product Hilbert space. You write it, you decompose it in full glory, and then you just transpose the second factor. So this is, let's say, it doesn't matter which one, but let's say transpose one of them, let's say the second part, and then means this guy should be unitary. Proof is very simple, but I leave it as an exercise, and we can work it out in the tutorials if you want. So then the second claim, so that these two claims actually are useful in general. They are not useful for they are not only useful for d equal to 2, but they are useful for in general. But in d equal to 2, we can explicitly facilitate them. So second claim, this is claim number 1. Claim number 2. If U dual unitary, let's call it just if U dual unitary, then U prime, which will be some V1 tensor V2, U1 tensor U2, where V1, V2, U1, and U2 are some single qubit gates, one qubit gates, unitaries. So if this guy is dual unitary, then U prime is also dual unitary. Is dual unitary. Means that we can simply dress any dual unitary with local unitaries and it still remains dual unitary. So the proof is very simple. You just take what does it mean to have dual unitarity, right? It means, I just go back now again to original picture. Dual unitary means that if I connect these two guys, then this reduces to two lines, right? The inner and outer half circle. Now, this is unitarity, right? This is U dagger. This is unitarity. Now, if I dress this unitarity by 4 gates, which are all unitary, now I will not even use symbols. I will just use daggers here, right? This is the same gate as here. This is the same gate as here because this is Hermitian adjoint, right? It has to transpose, it has to flip vertically, right? And now I do this. Now what I have is this guy against this guy is identity. This guy against this guy is identity. This is dual unitary. Sorry for this, but I'm a bit in a hurry. And then again, this guy is the same, so unitarity. This guy is the same, unitarity. You get this, right? So we are done, right? So everything just goes through. Single site unitaries are completely transparent for dual unitarity. Okay? So that's how we can now, I mean, we can actually use now these two claims to produce the most general expression for dual unitaries for qubits. I still have this book. No, I don't have, so I have to start cleaning. Okay, so now, yeah, I will just write it. So the third claim, which is my parameterization, claim any dual unitary for d equal to 2 gate for d equal to 2 can be written as some global phase, which is usually completely irrelevant, then V1 tensor V2 permutation times Z interaction. I can choose whichever I want. I chose ZZ, it could be XX, it could be YY, because here I have one side unitaries which can do a global rotation, so it doesn't matter. And that's it. So this guy, what are these guys? Now V1, V2, and U1, U2 are matrices, 2 by 2 matrices, which are in SU2. So these are SU2 matrices in fundamental representation. So arbitrary. So each one of them is parameterized by 3 parameters, right? We know we can write each SU2 rotation by 3 Euler angles. So 3 plus 3 plus 3 plus 3 is 12. Plus 1, global phase is 13, plus 1 is 14. We have 14 parameters. Now we can again compare it against the most general 2 by 2 gate, right, which is, I mean, 2 qubit gate, which is a unitary on 4-dimensional Hilbert space. That's U4, right? And U4 is a manifold of dimension 4 square, which is 16. So we're just missing 2 parameters out of this most general manifold, right? So we could say this is a codimension 2 manifold in unitary group, which is not a group, of course. Yeah? The product of dual unitary is not a dual unitary. That's, you have to be careful. I mean, not to claim something more. Okay, good. Any question? So now I could spend some time to tell you how, what you can do in higher dimensions. It's kind of a very interesting problem, and maybe you should ask Carol about this because it's related to other problems in quantum information theory. I mean, these dual unitary matrices, of course, are related to some other manifolds which are interesting. So what I want to say is that, I mean, for d larger than 2, there are no exact results. We have some numerical guesses of how the dimensionality of dual unitary manifold should scale. We have some extensions or some proposals. I mean, there is a literature. I mean, I will give references in my notes, but there are people, I mean, like Balázs Pocsgai, who has been thinking about this, proposing some most general ansatz, and so on and so forth. So maybe the key question is how many free parameters do we have? I mean, we have D. How many free parameters we have, right? We have U, D square, which is the general gate, general 2-qubit gate. This one has D to the 4 parameters, right? Now the question is how many free parameters do we have in a general dual unitary gate with D-dimensional Hilbert space? Well, I think our best conjecture now is it should be proportional to D cube. Now, so it means that when D grows, it actually becomes much smaller than D to the 4, but still it's large, yeah. But again, this is just a conjecture. It could be more, right? But conjecture is based on some numerics, and numerics seems to be quite confident. Okay, going back to our dual unitary dynamics. So this was just discussing single qubit gates, which is, as I said, equivalent to discussing single, well, in some sense equivalent to discussing some single qubit unital quantum channels, QDIT quantum channels. But now let's go back to the many-body dynamics. So out of this spectrum of these quantum channels, n plus and minus, which describe the decay of correlations along light rays, we could now discuss different levels of ergodic hierarchy. And I mean, of course, once we have the spectral decomposition, I'm going back to my spectral decomposition, which I proposed here. I can write the most general correlation function, right? Where I can write the term, the essential term in the correlation function. For example, the first term, which was n plus 2 power t of a, yeah. And this is basically just suppose that a and b are traceless. If they're traceless, then the first term doesn't contribute. So here I have a sum from 1 to d squared minus 1. And here we have lambda mu j. So now I will put a second index. Sorry, maybe I forgot here. Let's put a second index on the lambdas also, because there are two sets of lambdas, right? And there are two sets of eigenvectors, right? So let's put here a nu, and mu can be plus or minus. And now if you just look a little bit closely at this linear algebra, then you find that this is just, it's just, I mean, again, you can just use a vectorization picture in which this would be just a matrix element of this guy to power t between states, which are described by vectorized operators, which are described by states b and a, right? So you have to take the dot product or inner product of b with this guy and a with this guy, right? Which, again, doing the unvectorization means just the trace, right? Trace of an operator b and an operator which corresponds to eigenvector u, mu j, then trace of a, operator v, mu j, okay? And here this guy has to be put to power t. So you see, the most important thing is, of course, this behavior, right? And this means this decays exponentially for lambda j less than 1, right? So as soon as lambda nu j is less than 1, this term as a whole decays exponentially in time, which means we have exponential decay of correlations, which means we have exponential loss of memory of initial condition. Okay, and now we can basically just based on the collection of eigenvalues, lambda nu j goes from 1 to d squared minus 1. Just by looking at the collection of these non-trivial eigenvalues, let's call them non-trivial eigenvalues. Lambda nu j equals 0 is always 1. We forget about this guy. Looking at the non-trivial eigenvalues, just looking at the non-trivial eigenvalues, now we can have a set of very distinct behaviors, which we can now call a quantum ergodic hierarchy for dual unitary dynamics. So we can have, let's say, a ladder of behaviors. The first one is less ergodic, the last one is most ergodic. So first one is non-interacting. Which means, if all 2 times d squared minus 1 non-trivial eigenvalues lambda mu j are equal to 1. What does it mean? I mean, of course, this is a trivial degenerate example, but actually, we have immediately an example for that, which is the swap, right? When you take a swap, I mean, gates which are just a swap, which would be completely non-interacting. Actually, there could be a swap decorated by single-site unitaries. These single-site unitaries would not alter things. But if you take swap as an interaction, right, then you will get this situation in which all the eigenvalues are sitting here, right, at 1. So this is the complex lambda plane, right? I mean, maybe I should tell you if you have not heard about Markov chains in general, but the eigenvalues of a Markov chain are always within unit disk, right? I mean, if you have this kind of multiplicative Markov chain, eigenvalues or quantum stochastic matrix, eigenvalues are always inside unit disk, or on the boundary of unit disk, which is unit circle, or inside, right? They cannot be outside because that would mean that things could explode exponentially, but that cannot be because the thing conserves the positivity and trace, in particular the trace, so it cannot grow. Okay, the next level is non-ergodic but interacting. And interacting. So I will also plot a correlation function, typical correlation function. So for a typical correlation function of two trace 1 or observables which square to 1, or some which have correlation function which is 1 at time 1, here it just remains 1. Okay. So here it just remains 1. Now the second case, which I call non-ergodic and interacting, means that there are still few eigenvalues which are equal to 1. So there exists n larger or equal 1, such that, well, I can write it like that. There exists n such that n is larger or equal to 1, or smaller, strictly smaller than 2 times d squared minus 1, such that lambda nu j is equal to 1. But the rest of eigenvalues are, of course, well, they can be inside, they can be, well, elsewhere on the unit circle or inside unit circle. That means that since there are additional eigenvalue 1, that means that after a very long time, these terms will survive. They cannot decay, right? I mean, I should probably, it's over there, right? No, yeah, it's over there, right? So you see, I mean, there are terms there, right, which for lambda equal to 1 will not decay. So this will contribute to long time behavior, right? So it's something like, for people who have studied transport, it's something like a Drude weight, right? If there is a long time persistence of correlation, right, it's like you have a ballistic transport, which means you should have some sort of Drude weight, right? In this case, it's an overlap with some conserved charges, right? And these eigen operators of eigenvalue 1 are, morally speaking, just like conserved charges, right? You can connect them to existence of conserved charges. So which means that correlation function will decay, but then it might decay, might do some oscillation, whatever. Actually, this depends on, I don't want to be too picky, but this depends on whether these additional guys are on unit circle or within unit circle. If they are unit circle, there could be some persistent oscillations if you want. But let's not complicate too much, right? But generically, they are inside unit circles, so we'll have a picture like this. So let's see. There is a bunch of guys here, but then there are some guys inside. Number 3 is ergodic and not mixing. Ergodic but not mixing. That means that all the eigenvalues, all the non-trivial eigenvalues are away from 1, which means all non-trivial guys, of course I only talk about non-trivial guys, are different from 1 for j larger or equal 1, but there exists an eigenvalue that is absolute value is equal to 1. Okay? If there exists 1, there exists the other one because the eigenvalue have to come in complex conjugate pairs. But never mind. It's so it means that there will be some eigenvalues which are still on unit circle, and then some others could be inside. And of course, there is always eigenvalue 1, which is a trivial one. What does it mean? It means that in these terms there will be contributions like cosine t, cosine omega t, and sine omega t, which means they will never die, but they will oscillate. Which means that things can do something in the beginning, depending on the whole set of eigenvalues, but after these contributions of the inner eigenvalues die out, there will be perpetual oscillation. There will be oscillation which will not die, and no matter how long you wait, there will be memory of initial condition encoded in this oscillatory correlation function, or initial condition, initial operator in this case, encoded in this oscillation. I mean, you can think of this as a kind of super simple toy model of time crystal, right? I mean, people discuss time crystal in this business, in this field, and this would be like a kind of a most simple manifestation of a time crystal in an interacting many-body system. Okay, the most generic behavior is when all the eigenvalues take generic values, which means inside unit circle. This I will call ergodic unmixing. So all non-trivial unit circle for the J larger than 1 means there is a single guy here, and everybody else is here, which means that correlation decay exponentially does something non-universal, but then it decays exponentially. And now how quickly it decays is determined by the eigenvalue which is closest to unit circle. So the so-called determines the so-called spectral gap. Okay. Now, how am I doing? I mean, how much time do I still have? 7 minutes. 7 minutes. That's scary. Okay. So I suggest the following. I mean, I have prepared another lecture on random matrix spectral statistics in dual unitary circuits, and discussing spectral form factor. Luckily, Marin has already discussed spectral form factor, so I don't have to introduce it. So, which means that people know about it, what it is, and how it characterizes spectral correlations. So what I want to say at the end, maybe I just take a couple of concluding statements, and for those who are interested, we can discuss more about this in tutorials. So what else can we do? Now, I just scratched the surface of this kind of field, of this endeavor, and this is the simplest calculation one can do. It was the first calculation which we did with Bruno Bertini and Pavel Kos in 2019. But then, we and other people picked up and computed many other things. And, well, one thing which I already announced, which is to me the closest to my heart, is sort of a semi-proof. I mean, semi not in the sense that it's not rigorous, but semi in the sense we don't prove everything. Semi-proof of Bohigas, or I would prefer to call it quantum chaos conjecture for dual unitary circuits. Why I don't want to call it Bohigas conjecture is because it doesn't have nothing to do with classical chaos. Yet it's a very simple dynamical system with very few parameters, with very structured with local interaction and so on, for which we can show that spectral form factor should behave like random matrix theory in thermodynamic limit, which means we can only show statement about behavior of spectral form factor for large enough system and for short enough time. So we cannot show, we can only show the linear ramp of spectral form factor, in other words. We cannot show the convergence to the plateau. That's out of reach at the moment. Second thing which we cannot show still, even though we have good heuristic arguments, is fluctuations for spectral form factor. So going beyond spectral form factor, but looking at the fluctuations, which means this would be equivalent to discuss higher point correlation, spectral correlation functions, and proving that they also follow random matrix theory. This is something we have discussed in our papers, but it's not yet rigorous proof because there are some pieces of algebra missing to connect things. But these are interesting problems. I can talk about them more in my tutorial. I was also thinking to make a simple calculation. Maybe there's something I can do now is just to give you another exercise for the tutorial, which I want to do just to show you how natural it is to think about spectral form factor in spin chains. If you might think that this is a very strange problem for spin chains, okay, I will just give you one exercise. Think about how to compute what is spectral form factor. Let's say spectral form factor Marin already introduced it, but I will just repeat its definition, but I will specialize it on for non-Hamiltonian systems. I mean, for Hamiltonian systems, of course, you just take e to the minus e to the minus ith, right, where h is Hamiltonian, and take a trace of this and take a square. Now we don't have a Hamiltonian, but we have a dynamics, unitary dynamics. We have a circuit, which we denote by, I mean, like one time step of a circuit, which we denote by script u, and then we take the power t, and then we take a trace, and then we take a modulus square. And then we take an expectation value with respect to some randomness, some little bit of randomness. I mean, this is something that has to do with the fact that this object is not self-averaging, which means it doesn't make really sense for individual dynamical systems. You have to do some averaging, right? I mean, now Marin has averaged over time, I believe, or energy, anyway, energy ranges, right, which is kind of equivalent to averaging over time, a little bit moving time averages, and so on. But sometimes we can't do that, and we have to average over a couple of parameters in the model, which is not the same as doing random matrix theory, because this can be very, very, very restricted noise. But still, we have to introduce some artificial noise and average over it. Anyway, so now I want to do the following. I want to ask the following exercise. Let's take non-interacting spins. Let's take spins which are completely non-interacting on a line, 1, 2, up to L. And put them into random magnetic fields. So Hamiltonian would be like Hj sigma z j. So that's the Hamiltonian, non-interacting spins with random fields. And these guys will be random. Let's compute spectral form factor for that and show that it behaves like it's predicted for integrable systems. So that's just a kind of cute exercise to show that spectral form factor, k of t, should be proportional to, in my units, it should be just proportional to the L, that is the system size. Or if I divide by 1 or 2 to the L is proportional to 1. So there is nothing, spectral form factor is flat for this particular model. So that's kind of an exercise which we might discuss in the tutorial, and then we can say something more about how to approach this problem for interacting circuits like dual unitaries, and actually how to compute it. Okay, so then I think, well, let's maybe leave some time to, well, if there is still some time, maybe to take a couple of questions. Otherwise, I thank you for your attention.
Thank you very much. So, questions?
Thank you. So you are already using this machinery to study XXD model. Is it possible to gain some insight for many-body localization using this machine?
That's a good point. Thanks for asking. Yes, we can for sure exclude MBL in the dual unitary case. But of course, you can say dual unitary case is not generic, right? I mean, we have to fine-tune parameters. But in that case, since we can prove that we have random matrix spectral form factor, at least we can prove linear ramp. That is immediately proving, is the same as proving that there could be no localization. So we have, as I told you and hinted to you already, we introduced some disorder, which is arbitrarily strong. It turns out that for mathematical proof, it doesn't matter how strong disorder. We have to just introduce an epsilon disorder or double disorder of strength, whatever, order 1. And then we do thermodynamic limit. And in thermodynamic limit, we get a clean result. And then we can switch off disorder at the end. So which means we can, of course, disorder to 0 limit doesn't commute with the thermodynamic limit. So this means it's a particular statement about disordered system with weak disorder, let's say, but disorder doesn't need to be weak. It can be arbitrary, which means that in this dual unitary case, no system can localize. That's a statement, but yeah. And then if you ask me why I find it interesting, I mean, maybe I should have said that. Well, these dual unitary systems are indeed special, but you can try to perturb them. You can try to look at perturbations, right? I mean, people in theoretical physics, we are doing perturbation theory all the time. Why don't we perturb this situation rather than integrable situation? Because this situation is in many ways simpler than integrability. So we know more about it. We know all 2-point functions. They decay exponentially. So naively speaking, it's a perfect situation to do perturbation theory. So that's one thing which we have already attempted, not completely successfully, I mean partially successfully, but I think it's still a very interesting path to follow. To do perturbation theory around dual unitary circuits. And then I think one could prove that there are regions around dual unitary points for which there could be no localization, for example, because there has to be random matrix behavior. So it's like proving ergodicity around special points. I I mean, for those who have heard about some chaos theory in classical dynamical systems, there is this model I will talk about in the evening, which is called cat map, Arnold's cat. It's the same type of mathematics there, right? I mean, cat map has been established as a simple, rigorously proven model of chaos, and then mathematicians prove that it's also possible to have a neighborhood, the so-called perturbed cat, for which they can prove the same kind of topology of chaos. So, I mean, once you have a very strongly chaotic system you can control rigorously, I mean, then I think you have a good chance to do something more. I mean, and that's why I'm so excited still about this.